Hello and welcome to another video. Today we have a Prime B450M-A2 on our bench from Asus. I don't know what is wrong with this board. So let's start with the usual checks that we do. We go for resistance mode. We're going to be checking the 12 volt CPU connector. And this is high resistance. Then we're going to check that the 12 volt isn't shorted into the phases via the inductors, and it is not, so there's no MOSFET that is broken. Let's continue with the 24 pin then, 3.3 volts, high resistance, 5 VSB, high resistance, 12 volts, high resistance, and 5 volts high resistance. Let's see, can I see the 5 volts dual quickly? I don't think I can. Yeah, I don't find the 5 volts dual quickly, so let's not check that. But let's go over to passive power consumption and getting a CPU into here. And then go from there on, because in that state we can already tell a lot about this board. When we have the passive power consumption, especially with AM4 boards, the passive power consumption changes as soon as you have a CPU in there, because there's a line that's called CPU ID. That is being triggered by having a CPU in there, is either being pulled low or pulled high, and that activates some voltages, and we can have a look for them. And let's also quickly see how the BIOS battery is doing. 3.06 volts, that looks fine. So we're going to be starting out with a 2200G in this case. So CPU is in. Let's now see for our passive power consumption. So let's get this attached to here. So let's see now then. Let's turn on the power. And we have 150 milliamps, which looks very fine. What we would expect for AM4. So I'm attaching a speaker and a power button. And let's also get something where we can see some postcodes. This is an Asus board, which means that this has a COM debug port, and on that COM debug port you can just attach a flying lead, they call it, and get postcodes onto this thing here. So you need to connect pin 1 of each of the of this thing. You're going to be connecting pin 1 to pin 1 of the COM debug, and that should already give you something. And let's now see when pressing the power button. And there's nothing happening when pressing the power button. No reaction to the power button whatsoever. Okay, let's see if we have power on the power button even. Yeah, 3.3 volts is there. So that doesn't trigger anything. What we can do for the first thing, take out the BIOS battery and reset the BIOS, because the stuck BIOS or a bad BIOS can cause a board not to start up with the power button. So there's a clear CMOS header at the bottom right here, and I'm just shorting that. You can also short these two. And now again, getting power into here, shorting the power pins, and nothing. So that didn't help in any wise. So next thing I would do is check for damage around the SIO. For that we will need our microscope. So let's have a look at the SIO area, because the SIO is responsible for the startup for pulling voltages high and low. This is a rather small SIO in this case, and looks very clean around here. Yeah, no damage at all. Let's check for the let's check around this here. This is the main PCIe latch where I would want to check, because there's often damage here as well, but looks also clean. And then another point where very often you have damage is around the CPU socket itself. Just going over here quickly, just seeing if there's anything that we can find here. And area looks also clean. Another area that can have damage is the phase controller for the CPU. And it also looks clean. Let's go to the BIOS chip to see around the BIOS chip if anything is damaged. But nope, it all looks very clean here. No damage around the RTC section right here. So this should be 3VSB area. All of this looks fine as well. Now around the PCH. But everything seems to be fine. Let's have a look if we find anything around the back of the board. So this backside barely has any components. This is the CPU socket from behind, and it looks all fine. And then there's basically only components behind the chipset, but all of these look very clean as well. So let us check for some standby voltages. So I would want to see for the VDDP and the 1.8 volts of the BIOS chip. And the 1.8 volts is definitely running. Let's see, where's the VDDP located on this? This is probably 2.5 volts. This right here is probably supposed to be... Oh, this is another 1.8 volts. Okay. Let's see. This is probably 3VSB. Yeah, that's 3VSB. Where's VDDP located on this board? Cannot seem to locate it. So there's a 0.9 volt rail that is supposed to be here somewhere, which is a voltage for the CPU itself. But I cannot make out which one it's supposed to be. So while I was looking around, I noticed this. There had been work done here to this chip, and this chip got damaged. As you can see, the lower leg is bent, and the upper one seems to have been resoldered or something. So definitely a previous repair attempt. We will have to be careful and see if we can bend this back. So what I like to do, I like to take a razor blade for that, because that goes well in between those pins. And with that, it's very easy, as you just saw, to get them actually where they're supposed to be. But they're very weak already. Let's just see that we can solder them on now. And without breaking them any further than they already are. So just applying some flux here. So let's resolder this pad right here. This pin to the pad, I mean. So that is looking good. And now the upper one. That should also be fine. So just like that, we have a good connection again to the board with those pins. I would be interested why someone even attempted to do anything here. Like, how does that happen? Now I'm curious if there's any more damage anywhere here. So I'm not too sure if that component is necessary for anything, for startup, for example. So let's just try it out and see if we have different behavior now. So let's see now. Do we get a reaction to the power button? And we still do not. Okay, so that did not change. Sad. That could have been a good guess. Let me see in the board view where the VDDP is located on this board in order to see if that is running. So it seems that a lot of voltages are being created right here by this chip. So we will have to see for its outputs. I don't have a datasheet right now currently, but we're just going to be probing some of these pins. Let's see if we get any voltages here. because this thing is supposed to like have 105 volts on it somewhere, then the VDDP on here. Yeah, there's the VDDP, 09 volts, and there's also 2.5 volts supposed to be on this somewhere. There's the 2.5 volts, yep. And somewhere I think the 105 volts should also be on this chip here. No, no 105 volts. Okay, does this have... No, this is 1.8 volts. Where would our 1.05 volts be? So I cannot find 105 volts. Is it maybe this regulator right here? Let's check that. 09. That's a little bit low. That's not even a volt. Oh yeah, this is 105. Yep. That's then the feedback, that one, and that is the actual output. Okay, so that is also running. So next suspect that I would have, because I cannot see any more broken components physically, is to see if the BIOS has proper data in it or not. For that, we have right here a header where I can connect a custom-made cable in order to see the BIOS inside. I'll read out the BIOS while it's in circuit. So let me go to the PC and see if I can find anything abnormal or special with this one. Yeah, let me do that. I cannot believe this. This is the third chip. This is the third board of this person. And the third board that has a dead BIOS chip. What is happening here? The third board where I cannot flash the BIOS on here because you get a verification error at a specific address. What has this person done to their BIOS chips? So, time to get a new BIOS chip. These ones are expensive. These are the 1.8 volts 256 capacity ones. These cost quite some money, like for a chip. And I cannot believe I'm replacing a third BIOS chip on here. This is getting ridiculous. Well then, let me grab another chip just to see, and I will have to desolder the one that is on here. And yeah, taking it off the board and placing it onto an adapter or something doesn't make a difference. The chip is dead. There's no way to write to it anymore. You can read data off of it and save the data from it, but you cannot write from it anymore, to it anymore. So let's see for our BIOS chip here. Let's get Flux onto here. Get both sides fluxed up. We're going to be putting leaded solder on there, even though it doesn't really make too much sense here to put leaded solder on, because there's a ground pad underneath that we cannot flood with solder. So the highest melting point will anyways be the unleaded solder under the chip, and we will have to get that melted as well in order to take the chip off. So let's get some Kapton tape and let's protect that connector at least a little bit. And now taking tweezers and hot airing the chip off. And I instantly have a replacement here. We need bottom left, I think, is pin 1. So as always, when you're replacing BIOS chips, two important factors: the size of the memory, or maybe three: the size of the memory, the packaging that it's in, and the voltage, operating voltage of it. You can vary the size sometimes. You could botch something else into them, but I always try to go also with the same packaging. So let's get hot air for 475 degrees, but we're just going to be blasting this off. So the leaded solder is already melted and the solder below also melted quite well. Let's get leaded solder onto the center pad before we do anything else, in order to get some of the melting point down. Get some more flux in here again, some fresh. And now let's put on the new chip. So heating up the area, getting our solder melted. Now putting in our chip. And now let's see. This chip seems to be a little bit smaller. Not sure if this is the right. Not sure if we can get a proper connection with this. I didn't know that of these packages there's two different ones. Like, this seems to be a little bit too small. We might... Nah, I don't think we have we have contact here. Let's see now. Can I... Yeah, I might want a lot of solder on here in order to be able to get contact with the chip. Okay, that is too much solder. Let's get Flux into here again. And let's take some off of there. So I didn't know there was... I don't know what I ordered then. How did I manage to get a BIOS chip that is too small for that? That is weird. I wasn't aware of that fact that can be. So I will be testing if I can make this work or if we might need to take a proper size of this. So let me just do some tinkering. So I got the BIOS chip onto there and that didn't make a difference, and I got a chip to actually flash properly. And I would want now to go over a little bit more theoretical about how this works. So you have the power button from the front panel. And this power button needs to have 3.3 volts. This power button then goes to an ESD protection. This is not shorted to ground. This ESD protection only would, these are diodes that would clamp this voltage down to ground. So this is not shorted because we do know we have 3.3 volts here. Then we go to a 33 ohm resistor. I've had that these resistors go bad. And from the 33 ohm resistor, we go to two different places. One is a pull-up resistor, which is this 8.2 kilo ohm. This goes to 3 VSB, so this is a pull-up to 3 VSB. And the other side goes to the power button, which goes to a 1K ohm resistor into the SIO. This is the first thing you want to check after you've checked that you have 3.3 volts there. So what we do is we're going to measure this point now, or this pin, and we are going to be pushing the power button, and we expect this to be pulled down to ground. So let's try that. So we're now going to be checking the first pin of the SIO from this side, which goes to this resistor right here. So we see 3.3 volts here, and when we press the power button, it goes low. This is what we want to see. And you can check that on both sides of the resistor, just to be sure that it's actually reaching the SIO. We have right here 3.3 volts going low. This is a good sign, so that this is working. Let's go into the board view again for the next one. Next, what we want to check is a signal called 01 RSM RST. So RSM RST is a very important signal in order for the whole board to be able to restart, and for the SIO. The SIO has that on pin 42, or we can also see it on these resistors right here. And RSM RST is supposed to be 1.8 volts, and I had different mainboards that were missing this voltage why it wouldn't turn on. So let's check that now. So right here, RSM RST is on this resistor right here, and we see 1.8 volts. On here also 1.8 volts, and it should also be on this one 1.8 volts, and on that side 1.8 volts. Then you can also check that the RSM RST also reaches the socket, because having a broken socket can also be the case here. I've checked with the PCIe lane tester and with the DDR lane tester. The slot looks fine. All of the connections are there. So let's move on to the next thing. So the next signal is IO power button. And this is a signal that the SIO needs to put out, as far as I know. It has a pull-up resistor again here to 3 VSB, and then goes through 50 ohm resistor, goes to the socket. I think this is supposed to just have voltage on it, but I'm not too sure. So I think this should just have 3 VSB, and it might also go low as soon as you hit the power button. So let's see for that. And this is supposed to be the third pin of the SIO, which is this one. And let's see, if we press the power button, this also goes low. So this is an outgoing signal from the SIO. This should also be on that resistor right here, goes low. And on this side is always 3 VSB, and this side is the 50 ohm resistor. And we want to check that on this side also 3.3 volts is there, and it goes low when I hit the power button. So that also works like it should. So let's go further into the board view and see what else we have. The next thing that we can check is directly from the ATX PS on. So this is the pin, the green wire on your 24 pin that is supposed to be connected to ground. This one connects to a 33 ohm resistor and only 33 ohm resistor. This resistor then connects to a 20k ohm right here, which is a pull up again to 5 VSB. So you always want to see 5 volts on that 24 pin. And then it also goes to an N-channel MOSFET in this case. This N-channel MOSFET, you have gate at pin 1, and then you have pin 3 and pin 2 as drain and source. So if pin 1 has voltage, pin 2 and 3 are connected. What do we have here for signals? On the gate, we have O3 flashback. This is for this BIOS chip. This chip is there in order to be able to have the flashback function. So it turns the board partially on when you press that button right there. And that's why it needs control over the PS on circuit. And if this is faulty, this can also have problems and do mess with your power on state. So what we want to check is that we have continuity to these two, so that this is open, this and not open, that pin 2 and pin 3 are connected via the gate, because the gate is powered. Because what you have done is then pin 2 is the one that comes from the SIO right there. So if the SIO sees the signals, all of that it needs, it's going to pull this pin 33 low, which means it pulls this low, which then goes to that third pin and then pulls the PS on low to ground. So we want to check for voltages, and we especially want to check if this pulls it down. So we're going to check the pin right here, which has 3.3 volts. And when we press the power button, nothing happens. So it's already at the point that the SIO isn't giving out this signal. So we can also check for the N-channel MOSFET, which is here. So we see the gate has voltage. Our drain and source can be connected. And this 5 volts is what is supposed to be pulled down, but it is not when I press the power button. I'm pressing it down right now. What you can also check, if you don't have the 5 volts there, you would need to check close to your 24 pin adapter. In this case, it's right here. The cables are kind of in the way, but we have that resistor right there, which should have 5 volts on there, and the other side is supposed to have the 5 VSB on there. And then there's the 33 ohm, which needs 5 VSB on both sides also. And this is supposed to go low as soon as you press the power button. So the problem now we could isolate to the SIO itself, because the SIO isn't pulling PS on low, which it should do. So the SIO needs a few things in order to be able to do that. It waits for a few signals to arrive at it before it will pull PS on low. And one of those signals is sleep state ACE4. So let's see, sleep state ACE4, as far as I know, is going to be coming from the CPU itself. And we can check that on pin 34 and that resistor. So let's do that. So looking right now at pin 34, which will be this pad, 3.3 volts, and that 3.3 and that 3.3. So sleep state S4 is present. Another signal that is important is called power OKR. This is, as far as I know, a standby power. No, this is not the standby power. There's the standby power, but this one is connected through 3 volts, as you can see here. So this is not there in standby. So obviously you can also check the 3-volt battery and also the 3.3 volts coming into the chip. But we do see that the SIO puts out 3.3 volts into the power button. So those are present. And the next thing to check is S3. So we do not only have sleep state 4, but we also need sleep state S3. And we're going to check that on pin 29. So pin 29 is the 4th pin on the right side here. So this one, that goes there. And we can see 0.4. That is not right. Let's see. From this resistor, same. On the other side of the resistor, also nothing. So we are missing sleep state 3 in this case. And what we can do, we could test if this is the only problem, if we inject sleep state 3 and see how the board will be reacting. So let's try that. Let's go into the overview then again. So we are in the overview now. I will connect 3.3 volts via my lab bench power supply. So it's connected via that clamp to ground, and via my tweezers I'm going to be putting it on the board. So we're injecting 3.3 volts now, and have a look at that. The board auto starts. Oh, you cannot see the power consumption, but the power consumption is there. And it looks to be posting. If we get the post screen into here, we have a post. And as soon as I take it off, the voltage goes away again. The board isn't starting up anymore. So let me get the INA connected again so we can see that once more. So now we can see the power consumption. And have a look again. As soon as I put 3.3 volts into here, it's going to be starting up. And we have two amps, 4 amps, and a new picture. Boot logo. There it is. Question now is, where does the sleep state 3 come from? Because the problem is, as soon as you put voltage in, the board automatically starts. So every time you would start the board and injecting voltage, and you would need to hold it there, which is a problem. So let's see where sleep state 3 is supposed to come from and why it isn't starting, or if we might be able to figure out why it isn't starting, because it is definitely not shorted, because I see no power consumption on my lab bench power supply when injecting 3.3 the sleep state 3 with 3.3 volts. But I feel like there might be something before sleep state 3 that is missing, and we're just jumping over that with injecting it. So let's go into board view and see if we can figure this out. So the sleep state 3 is missing. Let's see where it's coming from. It has a single 300 ohm resistor. And on the other side of that 300 ohm resistor, let's see, we have one 10k ohm resistor. This 10k ohm resistor is connected to DDR VTT control, which goes to 1k ohm resistor, goes again to the control, and then goes to a P-channel MOSFET, I think. Or this might be a transistor. Yeah, I think this is a P-channel MOSFET that pulls something down. So this is just a gate, I think. Let me Google what this is, this part number. What if this is a MOSFET or a transistor? So if it's a NPN, PNP, or if it's an actual MOSFET. No, this is an NPN transistor. So this would be the base for the amplification, I think. Yeah, that's the base. Okay, so these two would be connected. So it's just a control circuit in this case. So it's not, the voltage wouldn't be coming from here for our sleep state 3. So this sleep state 3 is being used for a control circuit. Then let's see. For this 8.2k ohm resistor, we have a P1V05R. And we can see this goes to a dual N-channel MOSFET. And it again controls the gate. This pin 2 is the gate of a dual N-channel MOSFET. So the voltage is not coming from there. This is just being used here as a control. And then we can see another 8.2k ohm resistor. And again, it goes to pin 1 here, which means on this transistor, which means it's controlling a base again. So just being used as a control circuit. But it also goes to this N-channel MOSFET on its drain or source. We want that drain and source is not connected here between these two, because this would mean that the ground, which is here, would be connected to our sleep state 3 and would be pulling it low. So we want to see if on this gate, on the pin 1, we have voltage. We do not want to see voltage, or else it would pull our sleep state 3 low. So let's check on that pin right there if we have voltage. So let's see now if we have voltage right there. And we do not have any voltage there on this transistor, which means it is not being pulled low. We can also check that, yeah, there's some voltage here. But yeah, if this pin would have voltage, it would be pulled to ground. And if we now check the upper pin for resistance right here, we see it has high resistance, so it is not being pulled to ground. So let's go back to the board view. So all of this isn't necessary isn't important for us because it's not being pulled low by this. And then if we go back to where the sleep state comes from, the only other thing that is left is the CPU itself. So there's probably some signal missing for the CPU, which makes it not put out SLP S3. And I cannot tell you what that is. I've searched for quite some time, and I do not know what voltage is missing for the CPU in this case. Why it isn't putting out S3. So if you have any idea what the CPU all needs in order to be able to put out S3, feel free to leave it in the comments below, because I do not know. Like, I've checked the obvious things like having VDDP and the 1.8 standby voltage. Like, those are the obvious things to check what the CPU needs in order to be working. But I cannot figure out what else in this case the CPU needs in order to be putting out our sleep state S3. So I would want to do a little bit of a botch job on this. So there's two possibilities what we could do for a botch job. We would need a place where we have sleep state S3. For example, one place is right at the bottom, right here. That middle pin that you can see there, that carries S3. And what we could do, we could bound this S3 point to the 3 VSB. So as soon as the board turns on, as soon as you have 5 VSB, the board would instantly turn on, because you would always have 3 VSB on sleep state 3, which is definitely a botch. So you would always have to turn off and on your power supply in order to turn on the PC or not. What you also could do, you could do something that latches, for example. If you would take an actual switch, not a button, but a switch that you can permanently put in a different state, you could do it like that you connect a MOSFET to this point that takes 3 VSB on one side and then this as the output on the other side, and you can connect the button to the gate. Or you could just instantly, yeah, that just makes more sense. You can just instantly take the 3 VSB, connect it to one side of that switch, and then connect the other side to the 3 volt to the S3 state. And like that, you could use an actual switch and not a button in order to connect those two together and then have the board turn on via that. But all of that is a botch job because you cannot use it as a normal power button anymore. But you could do it through software, for example, for Windows to tell the board to shut down, then it could work. But then you would have to cycle it again in order to get the board to turn on again. So whatever you do, you will probably have to use your main ATX power supply in order to cycle the board to work. So what I will be doing now is I will be connecting this point to 3VSB, and then I will show you the behavior that it has. And yeah, we will go from there because I cannot spend any more time on this. I've been long enough at this board and I couldn't find why it isn't turning on, but this is a way to get this board somehow working. So let me show you that. What we're going to do, we need to go into the board view again, and we need to check what's the closest point to 3VSB and S3. So let's see for that. So in the board view now, we have this S3 point that we want. And now what we can do is we could check for just put in 3VSB and see what the closest pin to 3VSB is. And one of the closest would be this PCIe pin, because every PCIe carries also 3VSB, and you could connect these on the backside. So just run a wire from there to there on the backside, and with that have it being done. But let's scout for some more options. So the next one would be this resistor right here, where we have that. So let's check again 3VSB if we have anything close, but there's nothing close here. So let's check here if we have 3VSB somewhere here. And we would have 3VSB right there that we could also bridge to here. But that also wouldn't look as nice as, for example, doing it on the backside of the board. And let's see, we have this resistor right here. And I think there should be 3VSB very close to here somewhere. Yeah. You have the 3VSB directly above. So what we can do is we can bridge these two together, these two resistors, and just get permanent 3VSB onto here. So let's do that then. So just to be sure, we want the pin 30. That which is pinned to the third pin from the top needs to be connected with the fourth pin. But not directly the third pin, because you want the supply of that. So we can check where the supply comes to the 30 pin, and then we can connect this to the 29th pin, which is this 300 ohm resistor. So let's do that. So the pins that we are talking about is pin 30 here. This pin goes to that resistor right there, and on that side of the resistor we have the 3VSB standby supply, and we want pin 29, which is this resistor, and this is the side of the 300 ohm resistor that we want, and we need to bridge these two contacts with each other. So let's get some flux into here, and now let's get, with just a good amount of solder, let's see if we can bridge them together, or if we're going to be needing a wire. Nope, that's it. We got them bridged like that. And now we have the 3VSB always being put into the S3 state, so the board should always power up as soon as we apply voltage to it. So let's go into the overview and try this out. So let's see now. I'm going to be now putting the passive power on, and this should instantly start up. Oh, it reacts to the power button if we do that. Huh. Interesting. So I would have expected it to instantly start up as soon as we put power into there. And there's the boot screen. Let's see now. Okay, this is going into Windows instantly. I want to see how this reacts, because I would have expected that it instantly starts up, not when we press the power button. So let's see, the power consumption looks very good. We have 5 amps and we're going into Windows preparing devices. So let's quickly let that run through. So we are in Windows right now, and I want to know what happens when I push the power button. How does this react? So it does shut down. Let's see for the power consumption. Does it properly shut down? So it goes down to 500 milliamps, but the PS on is always on now. Because you can see the fan is still turning. Because the 12 volts are still applied, the PS on is still there. And when pressing the power button, it does react though to the power button and it will boot up. So that does work. But you will always have fan spin. Because all of the 12 volt fans are always turned on then. But it does react to the power button. And what you would need to do is, when it's turned off, you would need to actually cycle your power supply. And now you have no power consumption, no reaction, and no fan spin anymore. So the PS on is permanently pulled low when you do the modification like we did here. So in the end, you would still need to cycle this via the power button, or your fans would indefinitely run. Yeah, you maybe could do some modification to all of the fan headers with like with the MOSFET, when it's running, when it's not running, when it's being controlled. But yeah, this mainboard is not worth the effort for this. Like, the time I've put into this board is already way more than this board is worth. But I'm happy that I got to at least somewhat know what was wrong with this, so that the S3 is not being created but I do not know what signal the CPU is missing in order to be putting out that signal, that S3 signal. So yeah, but with this botch job, we were able to get it working, because this is now a functional mainboard. Not as you would expect it, but you could use it like that. And I'm sorry for the viewer that I couldn't get this any further, but I just I cannot spend any more time on this. So yeah, if you enjoyed the video, leave a like, hit the subscribe button. Thank you very much for watching. As always, all of my tools are linked in the video description. Thank you very much for watching. This was Mainboard Medic. Thank you very much and goodbye.